discussion to the sixth class in the LaRouche PAC class series on the new paradigm. Today will be the final class before our wrap up next week, which we'll say more about at the end of today's discussion. My name is Megan Beets, and I'm joined in the studio, as you see, by Jason Ross, who gave this wonderful class last week and will be leading our follow-up discussion.
We're also very happy to be joined by a live audience in Manhattan, who we will be hearing from. And we're very happy to be joined by you watching online. Now, last week, Jason addressed the issue of science, the crux of the matter. What is the human mind's relationship to the universe around us? What can the human mind know and discover? And how does the human mind discover it? And this really is one of the most crucial issues today as the humanity moves toward forming a new paradigm, a new renaissance. What are those universal principles which make us all human that all cultures can come together around? Now, since last week's class, Jason has sent out a number of homework questions, and many of you did take a stab at those. So Jason will be addressing those questions, getting some of your answers, going through those answers. And the purpose of today's class is a chance for you all to get feedback from Jason on your homework and also pose questions on the topics and the reading assignment that we perhaps didn't get to in last week's discussion. So we'll be taking live questions and live participation from Manhattan, and we're also taking live questions and participation from you watching online. If you are watching online, you can email your questions or comments into classes@larouchepac.com. And what we'd really like you to do is call into the conference line and ask your question or give your comment yourself. And you can do that by following the instructions on the class series page. So without further ado, I'm going to turn it over to Jason.
All right. Well, thanks, Megan. So I want to give a brief recap of some of the major themes from the discussion that we had last week, from the class last week. Take about 3 minutes doing that, and then we'll jump right into the questions. We're going to do that. We've got a number of question responses to the homework that came in via email, so we're going to alternate per question, reading a couple of those, seeing what we've got from Manhattan or the conference call line, and then discussing some responses to those. So overall, the theme last week was this relationship between the human mind and the universe as a whole. The miraculous fact that it is possible for us to use our minds to create concepts, human concepts, that are in a resemblance with nature such that we're able to use those concepts to transform our power in and over nature, our ability to discover physical principles that cause the effects of the world around us, and by using those principles as our own source of power to create new things that have never before existed, to create new states of matter, new compounds, new materials, new social structures, new technologies, all of this. This is what characterizes the human species. This is the basis of economics, not money. And this also has a connection with culture, in that culture, which very directly expresses a view of the human individual, a view of society, it gives an indication of some of the ways of gauging the relative values of cultural expressions. So in that discussion, we oriented around a paper that LaRouche wrote in 2003 called Visualizing the Complex Domain, which was the main homework reading assignment for this class. In that paper, LaRouche had pointed to Gauss's 1799 defense of the human ability to discover against what LaRouche called a satanic assault on the recognition of that capability by such as Euler, Lagrange, and the others that Gauss was fighting against. In that paper, LaRouche points to the discoveries of Kepler, of universal gravitation, of the motion of the planets, and of Pierre de Fermat about the refraction of light. So let's jump into the kinds of responses that we got to the homework questions. The first homework question was related to the example that we took up of Johannes Kepler. And so let me go ahead and read the question again. Basically, the question is, does the Earth go around the sun? And as it was put, The antiquated notion that the Earth is the center of the universe, neither moving nor rotating, serves as a common stand-in for previous false beliefs that have been overcome in the modern era. Yet, you may find yourself hard-pressed to explain to a 7-year-old how you know that the Earth moves around the sun. Could you explain this to a 7-year-old? Give it a shot. So let's watch a little video here. This is a, the typical image that I think many of us have in our minds about the solar system. There's a few things wrong with this image. One is that the planets are way, way too big. The sun is also way, way too big. And also those lines that you see there, we don't see those in the sky. Even with the best telescopes, we never see lines representing orbits that planets go around. So the way I'm going to do this, I'm going to read a couple of responses that came in from this homework, and then I'm going to go to Manhattan and just ask people. I think the mic will pick it up. We'll try it. Just call out, just shout out your thoughts. If it doesn't work, you'll have to come to the mic, but hopefully it'll work just picking up from the room. So let's take a look. This is one of the responses that came in. Someone wrote, I have to begin by saying not what I would say to a 7-year-old, but that I am that 7-year-old. Science has not been a major factor in my upbringing or my academic training. I've never seen anything like the drawings and manipulations before, and I'll need to see them some more and maybe read a whole lot more before I have anything to say to any 7-year-old on this topic. I enrolled in this course to learn things I didn't know, and the class is serving that purpose magnificently. One more response that came in about how do we know that the Earth goes around the sun? Someone else wrote in, yes, the Earth moves around the sun. I cannot explain why or how I know, yet I am convinced that the Earth moves around the sun. Ever since I can remember, I have never doubted that this is the way that it works. I'm not a scientist or scholar, nor have I engaged in any study or deep thought on this matter. After participating in this class series, I would answer, based on all human scientific study, observations, and discovery, I am convinced that the Earth moves around the sun. Not a very good answer, perhaps, but for me, this is the most reasonable and sensible conclusion. So let's hear it from our audience in Manhattan. Does anybody have any ideas about how you would sketch out explaining to a 7-year-old, how do you know that the Earth goes around the sun? Any thoughts? Yeah, go ahead. Okay.
Oh, good afternoon.
Hi.
I think uh, Earth makes a magnetic energy itself. The universe have a gravitation force. That's the Earth move around the sun.
All right. Any other responses? Any other thoughts about how we would explain this to a 7-year-old? Now, keep in mind that the question isn't why does the Earth go around the sun or what causes this, but also how would we explain that to somebody who might ask why a whole lot? Any other thoughts there?
I think in this way.
Yeah. I'm wondering if there's anyone else there who has any thoughts they'd like to add. Now, I can read a few more that came in via the homework. So actually, one of the responses that had come in is that this is what observation shows us, that if we go out and spend the night watching the stars, we see that they move all around, and that therefore we can conclude that the Earth is spinning, and this is why the stars move. That sounds like it might be a reasonable answer, except that really it's presuming the conclusion already. Just seeing the stars move around the sky doesn't indicate that the Earth is moving. Maybe the sky is moving. Let's watch a short video as we discuss this. So here's an image we got here. And it's okay, yeah, there it goes. Hopefully you can see it, or it's dark enough in the room there. This is what the sky looks like if you actually just go out and look at it. As your eyes adjust, you can see more and more stars. It starts to become apparent to you. And if you just watch it, you don't really see much happening. But if we fast forward and we look over the course of a night, see the stars are moving around. There's one star, I hope you can see, that isn't really moving. Or if it is moving, it's in a very slight amount. Also, these stars seem to be moving in a circle. Around that one star that seems stationary, if we draw this grid, as you can see, it looks like the other stars move around it in circles. So this is something that our senses tell us. It's something that we can watch and observe. If you went out and spent the night out watching, okay, good. If you watch that with a kid, they might say, well, looks like the stars are moving. It's pretty hard from just looking at this to come up with any reason whether you should say that the Earth is spinning or the stars or the sky are spinning. So I know that that answer had come in from a few people, that this kind of observation lets you know that the Earth is moving. It doesn't. Clearly people had seen this for thousands of years, and many people really did believe that the Earth was stationary and that the stars were moving around it. This observation in itself is insufficient for making it possible to determine what's occurring. If we put this in a little bit more context, we could even ask about what it means for something to be moving. So let me ask you this. If something's moving versus being at rest, don't you have to have something that you're comparing its motion to? That is, if a bus is going down the street, you'd say, oh, the bus is moving. Because compared to the street, which you figure is not moving, you know, the bus is driving down the road. Well, these images that we've seen of the solar system, of the planets on orbits going around the sun, clearly the street, the city, the whole planet, it's moving. It's spinning, it's revolving around the sun, we're given to believe, and we're going to talk about how we can actually come to know that. So the whole idea of saying whether something moves or not requires what you're measuring it against. So, you know, are we able to measure things as moving compared to space itself? Is there such a thing as space, which is not moving, and then things move within space? Not really. Not really. You know, Einstein covered this very thoroughly. Leibniz had a lot to say about this before that in the early 1700s. So I think that one of the things that this question brings up, does the Earth go around the sun, is not just what's moving versus what is still, but also what causes motion to occur. And that if you're asking what's causing an effect to come about, you can escape from the undecidability of trying to describe geometrically what moves and what doesn't by having more in your mind than motion, by having the cause of motion in your mind. So there's going to be a little bit more to say about this in the next question that we're going to take a look at. So the second question, and this is we're going to come back to say a little bit more about the first, is whether matching observations is the way that you know that a scientific theory is true. So the question was, before developing his physical theory of the planetary motions, Kepler created a very accurate mathematical model in the tradition of other astronomers. He called this his vicarious hypothesis. Yet, even though this model could say exactly where you would see a certain planet, Kepler did not believe that essentially perfect accuracy is what imbues a model with the truth. Kepler wrote, "The lack of any perceptible difference in effects between the as yet unknown true hypothesis and the false one assumed by us his mathematical model, does not make the effect identical. For there can be a small discrepancy which the senses do not perceive. So if matching observations within the bounds of experimental accuracy does not prove the accuracy or the validity of a theory, what does? What else could serve as a basis for knowledge? If it's not just matching experiments, what else lets us say that a scientific theory is true? What is a basis of knowledge? So a number of answers came in. One of the answers was that Google was the basis for knowing something. I think that that's probably what many people believe, even if they didn't send that in. At least it's the way we act most of the time. I'll just put up a short quote from Kepler. Kepler posed this very important question. He said, "Why is it so rather than otherwise?" Why is it so rather than otherwise? So I think if we think about that, you always have to, if you're saying that something is the way things are, this is the way the planets move, this is the physical theory behind it, you essentially have to be able to explain why something else isn't a better explanation. What makes your explanation better than others? So let me also ask, put you on the spot there, if anybody in Manhattan, including if you wrote in on the homework, that's fine, you can repeat yourself, did anybody there have any thoughts based on the reading and based on the discussion of Kepler? Anybody have any thoughts about what is the basis for saying that one theory is true compared to another? Is there more than matching our observations? What else is needed? Any thoughts?
I mean, one thing is that if you have your own hypothesis, then you can try to test that in the real universe, right? Isn't that one thing besides just what you're saying? Like, oh, these two things, I can't tell empirically if they're precise or not, but you can have an idea yourself and try to test that to see if it's true or not. Like when Kepler was doing in the New Astronomy, he talks about this puffy cheek image in his head, and it's kind of vague at first how he's thinking about it, but it's a new hypothesis than the idea of everything being a circle. Was eventually he starts saying it would be more of an ellipse than a circle, and he was saying that different planets have some ellipses that are almost identical to a circle, which if you were just looking from your vantage point yourself, you might just assume that it's a circle or something, but it's actually an ellipse. Is that
Yeah, well,
what you're talking about?
well, I think you brought up something interesting, Jared, because you said that it's not just that, you said it's not just about observations or empirical predictions, but then you also said, well, you make a hypothesis and you test it out. So I guess the question is, are there certain kinds of hypotheses that could be principles versus other ones that couldn't be? In other words, is it something about the form of a hypothesis that would let something be a principle versus a description? Or how are we able to, or maybe it's enough that if we put forward some kind of model, put forward some kind of mathematical relationship, and if it predicts very well what we end up observing, maybe that's all we need. Maybe that's how we know that something is true. Is that enough? Maybe it's enough. Anybody have any thoughts on that?
Just on that, in general, I think, I don't remember if it was Einstein's principle, but that the most simple explanation is usually the most adequate. I think that probably is part of it.
Yeah, that's certainly part of what Kepler thought. I just want to take a little look here at a few of the different models of how the planets moved in Kepler's day. So what we're seeing right now, This is a little bit exaggerated, but essentially this is what Ptolemy believed about how the planets move. So the green thing is the Earth. The yellow thing is the sun going around the Earth. The small red dot is Mars moving around the Earth, except that the big red dot is really Mars moving around a point, moving around the Earth. So this is, in rough view, this is Ptolemy's model. Now you can see if you look along the, oops, no, it's moving, hold on. Okay, see if it stays still, good. So along the line here, we've got, in the center, we've got the Earth. Up above it a little bit, the next black point is the center of Mars's orbit. And then above that, the next little black point is something called an equant. And the way it works is that this, this center, the small red dot around which Mars, the planet, moves, it moves around an orbit that's not really centered on the Earth, but is near it, and it moves at a speed based on that other point. So this was Ptolemy's system. It does end up making the planets move backwards and forwards and tracing out a very unusual path. What you see now is the path of the planet overall in space. So it makes this sort of bizarre winding motion that never doubles back on itself. That's Ptolemy's system. That's how he believed the planets moved. Now, if we compare him to the view of Copernicus here, so this is what we learn about in school as being the way things are. You got now, the fact that Mars is off-center like that, that's very exaggerated, but the planets have slightly different orbits. So here we've got the Earth in green going around the sun. This is Copernicus. And then Mars is also sort of going around the sun. The thing is that for Copernicus, the orbit of Mars, the largest circle that you see here is the orbit of Mars. And again, there's these 3 points that help to make it up. In the middle black point, that's the center of Mars's orbit. The one near the sun, that's actually the center of the Earth's orbit. So Copernicus didn't have the other planets go around the sun, actually. They moved around the center of the Earth's orbit. If you removed the sun, Copernicus's model would not change at all, because actually the sun itself has nothing to do with the motions of the Earth, Mars, Jupiter, of any of the planets. They have nothing to do with the sun. So the work that Kepler had done, he showed something pretty astonishing, which is that even if we change among the theories of these different astronomers, that we could go from the Ptolemaic system, which you see here, I'm going to pause it, where we have the sun and Mars going around the Earth. You could have the system of Tycho Brahe, according to which the sun, yellow, goes around the green Earth, with planet Mars going around the sun then. There's no difference, Kepler points out, between the Ptolemaic system and the Brahean system. You see that? Like the positions of the planets actually don't change at all among these two. And Kepler also showed that even if we go to the Copernican system, it doesn't change. It sort of changes the model. It changes the way you draw things, but you still observe the planets in the same place. So that is, among these 3 different systems, Ptolemy from 1500 years before, Tycho Brahe, Copernicus, although they seem to be different, Kepler showed that actually mathematically they were all equivalent. What that would mean is that none of these models as models could pass Kepler's test. Why is it so rather than otherwise? Jared had remarked how Kepler abandoned some of the principles that the other astronomers took for granted. Everybody assumed that all astronomical motions were based on circles, for example. Everyone thought that before Kepler. That's how everyone's models worked. Everyone believed that motion had to be based on some kind of a uniform motion. Everyone thought that. Everybody before Kepler. So Kepler used their concepts and said, fine, let's try it out. And he made a model that worked pretty well, very well as astronomers could observe back then, but he knew it included some erroneous assumptions. So he said that if the only way you can make this kind of model match the data is to include in it distances that aren't right, then this whole approach is wrong. And so what Kepler did, he really asked a very different question. He didn't ask, what's the model that best matches things? He asked, why did the planets move? And I think that someone was bringing that up. Also, this hypothesis about a magnet. Kepler believed that there was something magnetic in the answer here. Here's one of the answers that came in on the homework. Somebody wrote in, I think this was Martin, the assumption that a perfect mathematical accuracy of formulas could be a proof for our knowledge puts the causality in the numbers. But can this be? The ultimate question is causality, where Kepler differed from believers in numbers. So we've got some thoughts there, using this to then go back to whether the Earth goes around the sun or vice versa. The way Kepler answered this was totally different than the way Copernicus did. Kepler said that the sun isn't just sitting in the middle watching planets go around it, but that the sun is causing the motions of the planets. Kepler had a physical theory for this. He said that the closer a planet got to the sun, the faster it would go. The further it got from the sun, the more it would slow down. He didn't even have the ability to write down mathematically his concept. So he had a concept that couldn't be expressed in the language of mathematics. Not exactly, but for him, the physical principle came first, even if you couldn't exactly write it down. So this is something that makes Kepler's view different from all the others, is that he said we're going to use a physical cause for the motions, and we're going to understand appearances not as being caused by observable or imagined sensible things like circles, but by physical causes. A result of that is that he ended up concluding that the planets moved in ellipses. Not by testing out the shape of an ellipse, but from his hypothesis about what would cause the planets to come closer to or farther from the sun, combined with his physical thought about how the sun was causing the motions, the speeds to change, the result of those things combined was an ellipse. So that's how Kepler got to his geometric conclusion. Came from a physical cause.
Can I just interject here?
Sure.
Bob wrote in the meantime about how he would explain to a 7-year-old, and he said, I would not try to explain. I would give a physical demonstration using a rope and gently spinning with me and the child at opposite ends. Our physical sizes and weight difference would represent the gravitational mass, and I believe the child would have an experience of this.
Yeah, that's true. Yeah, two people spinning around each other. From each viewpoint, the other one seems to move. The sun seems to move around us. If you're standing on the sun, the Earth would seem to move around you. And I guess since he's bigger, he's probably going to move less as they're spinning around. So that's not a bad idea. It's a good description. I wanted to read a couple others that had come in. Let's see here. Okay, read that one. Okay, I think that's fine. Let's move on to the next. We'll move on to the next question here. So that question was about final cause, and it was specifically a question about Fermat. So Fermat, as you remember from last time, described that the way light moves, as it moves, say, from air into water, is that its total path, the overall path, was the path that took the least amount of time. And Claude Claire-Cellier, the leading Cartesian at the time, vehemently disagreed with Fermat. This is what Claire-Cellier wrote. He said to Fermat, the principle you take as the basis of your proof, namely that nature always acts by the shortest and simplest path, is only a moral principle, not a physical one. It is not and cannot be the cause of any effect in nature. This principle cannot be the cause, for otherwise we would be attributing knowledge to nature. That is, knowledge of which path would achieve the goal of moving in the least time. And here, by nature, says Claire Sellier, we understand only that order and lawfulness in the world, such as it is, which acts without foreknowledge, without choice, but by a necessary determination. So the question was simply to respond. In other words, to lay out what your thoughts are on whether Fermat's idea that light takes the least amount of time could be a principle, or if that challenges your idea of what a scientific principle would be. So a few comments had come in. One of them was that Fermat's principle challenges my idea of what a scientific principle is. Another student wrote in, what accounts for the creation of the operative laws of the universe? Don't laws require a lawmaker? How could we create physical principles without the moral principle of the good or bettering? Is development a principle of the universe? If so, then the individual laws aren't the entirety of its substance. So those were some of the thoughts that came in. I'm curious whether anybody in Manhattan has any thoughts about this. What do you think about Claire Sellier's view that the idea that light will take the least time? Claire Sellier thought that's not scientific. Knowledge doesn't have a purpose, and knowledge doesn't have knowledge about the future. Nature only acts every moment. How would you respond? What do you think of Claire Sellier's view? Uh-huh. Yeah, I think it's not going to work too well without the mic.
All right. I can't even get to the scientific question because my mind is having a hard time. How do you know how come that path is the quickest, the least amount of time? Why does that particular angle serve to be the shortest time? For the light, you understand what I'm asking, right?
Oh, in other words, how do you turn the idea of least time into a specific angle?
There's something about how come time how come that particular angle is the fastest time? Why didn't it go 2 degrees up or 2 degrees down? How come? Is it about the angle or the degree of angle and degrees in the angle? That's
great. Okay, got it. That's I'm glad you asked. Let's put the picture up just for a moment here. So I'll say what the effect is or what the formula is, and then talk about how that got shown. So the way it works is that from the point above to the point below, if we take each of those points and then measure how far it is from a vertical line, so whatever this distance is here, compared to the point below the water, we can measure this horizontal distance. The distance in the air compared to the distance in the water has a ratio of 4 to 3. That's what gets observed. That's not an answer to your question. I just wanted to at least put forward like what the principle is. In other words, that's the way that light bends. Whenever you go from air into water and you start and end on this circle at equal distances from the point where the light reaches the water, the horizontal amounts in the air compared to the horizontal amount in the water always has a ratio of 4 to 3. So the question then is, though, why would that result from the idea that light should take the least time? Now, so Fermat thought of this principle in 1657 because a friend of his had written a book about light, and he explained reflection by light taking a path of least distance. And I kind of showed a short video explaining why that was true last time. We could talk about it more too. Fermat said, oh, okay, well, when light goes from air into water or into glass, it moves at a different speed. So instead of just looking at the shortest distance, we should look at the amount of time it takes for light to achieve its action, to do what it's doing, to reach its destination. And so Fermat had this idea. He said, well, for example, if we look at this picture again, imagine that light had gone directly from the initial point above the water to the lower point. If light went straight from here down to this spot, it'll intersect, I hope you can see the cursor, it'll intersect right about here. That's where it'll enter the water. If light took that path, it would be shorter, but it'll also spend a little bit more time in the water. So the question is, the fact that overall the path is shorter, but you're spending more time in the water and a little bit less time in the air, when it's slower to go through water than through air, there's one spot where it's just going to come out the best, where the path has to be a little longer than the shortest path, but by doing that, you get to spend more time in the air where you go quicker and a little bit less time in the water. So that was Fermat's idea. It took him 5 years before he did the math to show that the result, let's say from air to water, is this 4:3 ratio, or just the fact that there is a ratio between air and water or air and glass. The ratio is different depending on what you're moving through, but the fact that that ratio coincides with the concept or results from the concept that light takes the least time. It took him 5 years before he did the math to show that. I did not prepare slides on showing how you can derive it from that. It definitely uses calculus, but it really only is a few steps with Leibniz's calculus, but I don't have slides or formulas to show.
In other words, if you know the 4:3 ratio, you could figure backwards if you don't have a stopwatch to measure how fast it goes through the water.
Yeah, right. So, I mean, nobody was able to measure speeds back at this time in the 1600s. In fact, almost everybody thought light moved instantly. The fact that Fermat said light took time to move, a lot of his friends said, you're crazy. Light's instant. You know, people did experiments where two people with lanterns would stand on hills far apart from each other. And, they'd open up the shutter on the lantern, to like make a Morse code flash. And then the person on the other mountain would open theirs when they see it. And then, you'd basically have a sense of how long it took. And if the mountains were close or they were far, it didn't really make any difference when people did these experiments. So they said, well, light moves instantly. It doesn't, but it's very hard to measure. I mean, I know I'm not fully answering your question, but I think the intuitive part about it is that.
But you're also saying there are many other things being discovered, as in the description of one man on one mountain with a light and one man on another. Many things are just sort of coming to people's awareness, discovery, putting into words what the laws are, what the physical, what one is seeing.
Mm-hmm. No, a lot
so
came
much
together.
more. So much more. Yeah.
Right. No, a lot came together. Experiments. I mean, people had been able to measure that light bent when it entered water. People knew that for, thousands. People always knew that. If you do any fishing or you just go in water, it's kind of hard to miss. So people saw that, but it really wasn't until the 1600s that a formula was ever really discovered or written down. And Claire Cellier basically stole the formula and printed it first. Descartes stole the formula, got the formula printed in a book first so that he claimed that he discovered it. But the fact that there's a ratio between those horizontal amounts, that came first from observations, just noticing that. Then the question was, well, but why does that happen? And Descartes had that stupid idea with the tennis rackets. Fermat had the idea that light always moves in a way that takes the least time, which does result in what we observe. So in other words, you can make a formula that's right. So a man named Snell in the Netherlands, he had figured that out. Descartes was at the college where Snell worked, and he heard about the formula. And then Descartes basically printed a book where, to take credit for the formula, he had to explain why that formula works. So he came up with a really stupid physical theory. And then Fermat came up with his own physical theory. And at first, he thought that he was wrong because he assumed that it would actually make light bend in a different way. So it wasn't for 5 years until his friends were bugging him that he did the math using a mathematical technique that he developed to be able to say, hey, my idea of light taking the least time, it turns into these ratios between these horizontal distances. So yeah, a lot came together. It was a place where observations were really behind the thought. Fermat never observed that light took any time to move in air or water, but he still, based on this concept, this principle, had that hypothesis. And he was right. Light does move slower in water than it does in air. And the ratio of the speeds is 4 to 3, just like the ratio of those horizontal distances. Does that help? Do you have any more questions about that?
That was very helpful to me.
Okay. You know, what we can do is, I'm not sure what the best forum would be for it, but maybe I'll like make a little PowerPoint and add it to this class page that shows for people who are can follow the calculus steps, how you go from Fermat's principle to the horizontal distance ratio thing. But here's the thing is that people, like what Claire Sellier said, which is that, hey, nature doesn't have an idea of an overall objective. Nature just acts at every single moment. So if the idea is it's gonna take the least time, doesn't that mean that nature's thinking about the future? How could that be? So I wanted to use another example here. So I've got we'll see how this shows up. I've got a ball here and a piece of string. I want to take something similar where, okay, so first off, does anybody have an idea about how to define what a straight line is? How do we know whether a line is straight? Any answers? Any thoughts on that?
It's the shortest distance between two dots is what I learned so early on. But
shortest distance.
I'll take it.
Okay, I like that answer. Let's go with that one for now. We can consider some others, but let's work from that idea for now. It's a much better answer than because it lines up with the ruler. Because you say, well, how do you know the ruler is straight? So, okay, shortest distance, we'll go with that. So it just so happens that if you were wrapping a string around something, like here I've got a rugby ball. All right, so hopefully you can see this pretty well. Okay, so I've got 2 spots where my fingers are holding it, right? And between them, I've got the string pulled pretty taut. If I put my fingers in places, let's say I put it like this, so the string's sitting like this. That is not a very straight line on the surface of this rugby ball because I could pull the string tauter, right? There we go. Now it's nice and tight, and that's what we could call a straight line on this, admittedly, we would say a curved structure. So that's an overall concept of what a straight line is. But we do have a way at every moment of extending a line so that it stays as short as possible. So, and you can try this at home with whatever you've got, strings and, vases, jugs, balls, just, your pet cat, whatever you got. If you start wrapping the string around, so I've started pulling it and it's taut. So at this point, I could choose where do I put the next portion of the string. Do I put it over here? Do I put it over on this side? Do I put it straight down? Let's say I put it over here. If I added the next little tiny bit of string and I put it over here, like that. That's not right, because to get there, I could have, this is a little awkward, okay. There we go, okay. If this is where I was supposed to go, well, that's not right, because I could have reached this point more directly with this more diagonal line. Maybe I'll leave this for you to try at home. I don't think this is working that well here. But if you're wrapping a string around an object like that, you'll just feel that there's one way to continue wrapping it that won't make it slip or that won't change what you had before. There's a way to extend a string such that the overall wrapping that you make is the shortest one of all possible ones. So Fermat's principle about light, that it takes the least time, it is an overall concept, but it also, through Leibniz's calculus, it also provides a way, and further developments of the calculus, it does provide a way to say what is going to happen at every moment. but it does it not by focusing on each moment, but by an overall condition or an overall objective that it fills. And so today, the principle of least action, which is a more developed concept based from Leibniz, from Fermat's idea of least time, today, the principle of least action is the most fundamental way of understanding all of physics. It's like the way that pulls all the laws of physics together into one. So, Claire Cellier didn't like this idea. Many people, it rubs the wrong way that there's some kind of overall intent, seemingly, that nature observes. But that's how it is. And I think we should reflect on that and say, well, what does it tell us about nature that even something as simple as the motion of light seems to be trying to achieve something? That has a very major, I think, similarity to the way our minds work. And we do find it as a principle of nature. So now there's much more that could be said on that subject. Okay. Any other thoughts on that topic before we move on to the next homework question, or any other thoughts that came to mind about the previous ones, like how do we know the Earth goes around the sun? If we know that the Earth goes around the sun? Okay. All right. Well, feel free to chime in if you want to. So let's move ahead then to the fourth homework question. So this one was pretty straightforward and open-ended. The question was just, what do you consider to be the greatest scientific discovery or technological advancement, and why? So I'll put up a few of the answers that came in here. Somebody wrote in saying the discovery of fire, which has then led on to nuclear power, the creation of new energy. Well, that's a pretty good answer. This is, if you look historically at what first set the human species apart from all other life, I think the earliest thing you can really point to is the use of fire. We're the only species who does that. Another answer that came in was the discovery that the universe is creative, the discovery by Prometheus. This person wrote in, I think Martin, everything comes from our self-conception. Are we an active force in our willful advancement? Another response, electricity. Ben Franklin is the American Prometheus because he stole this electrical fire and shared it with mankind. Would the American Revolution have occurred without Franklin and his work? One more. Somebody wrote in the good and the search for truth. The discovery that those are not distinct concepts, but are very connected. And this comes up in the Plato. I included a very short excerpt from Plato's Republic for the reading for this class. There was that LaRouche paper and then a little bit from the Republic. And this concept is included there. The connection between the good and the search for truth. Looks like we've got another response in Manhattan. Go ahead. Is this your idea of the greatest discovery?
I think when universe have always the gravitational force, when when Earth makes electromagnetic force, the gravitational force push the Earth. There's a verticalization. There's a Earth is moving.
Okay. Looks like there's another response there. Mm-hmm.
Another, when sun reflect the water, the water component is triangle shaped. When light through the triangle shaped, he throw the 45-degree angle.
Okay. Looks like there's another response there. Let's hear that one too.
Oh, no,
Thank you.
I was just saying that for the greatest discovery is the well, they already had it, the principle of the higher hypothesis. hypothesis of the higher hypothesis, which is was in the Greek Renaissance, or the Greek Plato's conception of the good, and the revival, which became the Italian Renaissance. So,
Okay. I think that's a good collection of them. I mean, between fire, electricity, you might say it's a form of fire, but then very importantly that, I mean, think about what a discovery, maybe even discovery might be a strong word if you don't agree with us, but let's call it a discovery. The discovery that there's a coherence between good and knowledge. That in the search for the truth, people are good and do good, and that a culture oriented around that is a good one. So I think at this point, those were the main questions that I had on the homeworks. I know that there might be some other questions that have come in via email or just other questions in general on these topics. Any?
Yeah, so why don't we do this? I'm going to read, well, I have several questions that have come in by email. We can also start to take some more general questions from Manhattan. But let me just say first, if you're watching online and you have a question or comment, you can either email it into classes@larouchepac.com, or you can call into the conference line that we have hooked into this broadcast and ask it yourself. And the instructions for doing that are on the class series webpage. So why don't I begin with a question that came in. It's two questions on the same topic that came in via email. And while I'm asking and while Jason's answering, maybe we can get some questions lined up in Manhattan. But they're on the topic of the calculus.
Mm-hmm.
So the first question, which is more general, says, can you give a short conceptual idea of what Leibniz's calculus is about and what the infinitesimal is? And then Oswaldo has a slightly more specific question and insight into it. He says, if I remember well, Leibniz named his development as differential calculus instead of infinitesimal calculus, given his approach of using the calculus of differences and taking them as a ratio of related variables, taking the one at the denominator, to a very small difference and obtaining a 0/0 indetermination, which process-wise turns out to be a finite quantity. I was very happy when you used the word language in addressing the process of inventing a mode of expression when referring to mathematics, because in this particular case, it is the mind's representation of an abstract process that can be matched to a physical process, and then provides a tool to advance the human thinking capacity. Would you comment on this idea in the sense of a tool that handles differentials infinitely tending to 0? And also, he adds, the terror of Russell, Kronecker, and then Hilbert trying to dispose of the infinitesimal as a natural attribute of the human mind.
Okay. Well, I was afraid that I might have gotten a little bit overly mathematical with it last time. I know that some of the question about the calculus had come up last time. So I wanted to do it today was respond to this with a little bit more about the catenary, which I really like because the catenary allows us to look at change not being related to time, because the catenary doesn't move, but it does allow us to talk about the very different concepts of the forces in the chain and then the shape of the chain. And I think this will also address the question about differentials or infinitesimals or 0/0s and what that means and why that comes about. So let's okay, so we'll take a catenary here, and I might engage Megan's help with this in just a moment. So when we're holding up a chain here, and there you go, maybe you can just grab a piece of that there. Okay, great. So here's our
Maybe we can get the wide shot again.
yeah. Okay, great. So here we've got a catenary. Now, could you hold the two perpendicular? Yeah. It's a little long here. Let's see if we can get out to the side far enough. Okay, great. Okay. All right. You know what? This is just a little bit too long. How about, can you just hold this so that we just have a bottom piece and then forget the rest? Okay, great. So now let's take a look at what's going on in terms of how we're keeping this chain from falling on the ground. If we were not applying any pressure to this chain, meaning if we both let go, I think we all know what would happen. It would fall, so we're not going to do that. Now let's take a look at the relative portions of the amount of pull that Megan and I are applying to this chain here. So I hope you can see these strings okay. Up here where the chain is ending, I'm both pulling up and I'm also pulling horizontally. If I don't pull horizontally enough, the chain's going to want to sag inwards. So I have to hold it out here. And by keeping these two strings at 90 degrees, I'm able to really separate the horizontal pull and the vertical pull. The horizontal pull that I'm exerting is the same as what Megan's doing. Megan's only holding the chain horizontally. She's not lifting it up, except for the fact that the rest of the chain is hanging down, so it is. But, okay. The vertical amount of pull that I've got to exert here, well, I'm holding up the whole chain. Megan's not holding up the chain. It's flimsy. If I let go of it, it's not like there's anything Megan can do down there that's going to keep the rest of these links staying up in the air. That's entirely the vertical string that I've got over here. So let's take a look at some pictures now about what happens as we extend the catenary and make it get longer. So here's a view of the infinitesimal. So first off, here's the catenary that you just saw. So Megan is holding the part down there at the bottom that's horizontal. I was holding the part up at the top. Let's look at the chain if it's not quite so long. What we're going to do is we're going to grow out the chain. We're going to keep adding one more link to it as it extends itself. So if the chain was shorter, like this, these are different colors. I'm not sure how apparent that is, but the horizontal pulls exerted by both Megan and then by me, those are the white horizontal arrows, and they're the same. The chain itself weighs something, and that blue arrow, the vertical portion of the two strings that I had, where I held the catenary not just at one point, but with those two strings, that vertical amount is the same as the weight of the catenary. The upper person is holding up the catenary to keep it from falling on the ground. The lower point really is only being pulled horizontally. If we make the catenary longer, so now its full length is this orangish color, and the arrow up top, as you'll see, the horizontal arrows are the same. As we keep extending the catenary, the horizontal amount remains the same, but the orange length, with that full length of the catenary there, it's about twice as much as the amount of vertical pull required when the catenary is only this long, before we've extended and added the rest of the links to it to double its length. So what we're able to express as an infinitesimal is that the ratio then between the, what's the best way to hold this? It's kind of hard to see. So the ratio between, can you pull it a little bit? It doesn't have to be on camera, but just, yeah, good. So the, hold a little lower maybe. Okay, there we go. So the ratio between the amount of horizontal pull and vertical pull, it changes exactly based on the number of links. That is, the ratio of the vertical to the horizontal is in a ratio based on how long the chain is. So let's take a look at what we've got here. So from the, okay, so let's count up a certain number. So let's, how many links do we have total here? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 16, 18. So let's say 20. Got 20 links here. Let's go back halfway. 1, 2, 3, 4, 5, 6, no, 2, 4, 6, 8, 10. Okay, so we're down here. If you take a look at the angles at the links down here, and then the link up here, down here, if you look at the way that the chain is extending itself right here, I think it's pretty much at a 45-degree angle. That the amount of horizontal is the same as the amount of vertical. So if what I've just gone through with this little bit of physics is true, up here with twice as much chain, the amount of vertical should be twice the amount of horizontal. And so I kind of leave that to your imagination, whether it looks like if I put a triangle here, that is twice as tall as it is wide, would that match sort of the slope of the catenary at this point? And I think it would. This is another wonderful thing to do with your friends and measure out the number of links and see if every time you add, if you double the number of links, that the triangle that reflects the slope right there gets twice as tall, twice as vertical. So here's the thing. As soon as you actually add one link to the chain, the slope changes because now the chain is longer. So the Leibniz-style differential, a ratio of infinitesimals, the differential here is that ratio between vertical and horizontal is the length of the chain compared to a constant. dy over dx is proportional to the length of the chain in Leibniz's terminology. That's a statement that is only true if you don't actually add any more to the chain. As soon as you add a few links, it just got heavier. And now at the new extremity, after the links that you have added, the ratio is changed. So it's something that's only true, you might say, at that moment as an intention of how you grow the catenary. But that if you actually grow it a finite amount by adding a link or two, it's no longer valid. It's no longer, the previous ratio is no longer accurate. You have to redefine the ratio based on the new length. So I think what we got here is a language that lets us put two things together that are very different. Forces, things that you feel, tensions in strings, you could measure with springs and scales, and then an actual shape of a chain. Those are very different things, aren't they? Oops. A shape of a chain is something very different from a tension. But with the infinitesimal calculus, the differential calculus with Leibniz's development, we're able to put those two together. And this was something that Kepler was unable to do. He had something very similar to the way that the ratio keeps changing as we add more links. Kepler had this idea that the speed of a planet changes with how close it is to the sun. But part of its motion is also changing how close it is to the sun. So as it moves, the way that it's moving keeps changing at all times. So except at the moment where it's farthest away from the sun or closest to it, it's always changing. So we need a new language that lets us combine two things, the actual path of the orbit and a physical concept where the speed changes based on how far it is from the sun. So that's the real power of the calculus there. And then, in Oswaldo's question about why did people get so freaked out about this, why do they say that there is no such thing as change or speed in calculus textbooks? This began before Hilbert in 1900, but it's definitely along the same kind of direction, where the view was, if it's not something that you can observe at a moment, it's not real. That a bus has a position at a certain point in time, but it never has a speed because change doesn't exist. I don't know how they would, time is a tough thing, but with a catenary, I don't know how you're going to claim that the change doesn't exist. It's a very simple ratio of forces of holding the chain up. So anyway, that's what I can say about that on the calculus.
Okay. So why don't we go to Manhattan and see if there's a question there. And while that person is getting up to the microphone, I'll just remind people you can email your questions in if you're watching online to classes@larouchepac.com. You can call into our conference line, and if you're in the conference line and would like to ask a question, you hit *6 to get in the queue so we know that you have something you want to ask or say. So why don't we go to Manhattan?
Yeah, hi, Jason. This isn't a technical discovery, but it was an important discovery for me that I didn't have before working or becoming involved with the organization. And that is, whenever it was, there was a point where man discovered that he could both create and shape the future. I remember Helga years ago in a conference that we had, she played an excerpt of the song "Que Sera Sera," And so this goes along the lines of British imperialism, which many of our citizens have that tendency, kind of paycheck to paycheck, or listen, right? It's out of our hands. And so for me, from the portions of Lynn's book on Earth the Next 50 Years was the first time I was really able to actually begin to think in those terms. As the paradigm shift grows and develops, when you talk to people about this, it's a discovery for them because they like to think that, but they just haven't. So that trap of British imperialism that we need to break, I think, for just the idea that you can shape and create the future. And the best way to do that is to rally around us, is what comes to mind when we talked about discoveries.
Mm-hmm.
Okay, is there another question there in Manhattan? Looks like it.
Yes, I have a question. I was just reflecting, and I would like you to say something about the difference because we're talking about now hypersonic speeds, for example. And one thing that this causes me to think about in terms of the shape of the universe is the difference between sound, how sound propagates, how light propagates and travels, and now the recent discovery of gravitational waves. If you could say something about those three things and how they are different or similar.
Hypersonic, and then the light and gravity waves.
Yeah, and waves versus particles, and
Oh,
I mean,
yeah.
because they all have very different qualities.
Yeah, so the as far as like how light operates, nobody who treated light as a particle was able to come up with a good explanation about why it bends, why its path bends. So Fermat's principle makes sense, and because it doesn't treat what's occurring at each moment, it's about an overall principle. With the development of the wave theory of light by Huygens later in the 1600s, he explained light, as he said, he knew how water waves worked. Water's a wave can move through water without really moving the water, but it's got certain characteristics. As the water gets shallower, the waves change. Anyway, so Huygens had a whole theory about light, that the color of light, for example, was based on how closely spaced the waves were. And what Huygens did was purely based on the speed of light slowing down when it enters water. He showed how light as a wavefront would naturally go ahead and bend as it moved into water because of the speeds. Like you might imagine it's kind of awkward, but let's say you got like a truck that's driving and it's entering water. Okay, as the first wheels. Okay, here we go. Rectangle's better. Okay. Okay, so this wheel's already in the water. The one that's still up here on land, let's say it gets better grip. So as the truck's moving, at this point, part of it's in the water, the part that's still on land is getting better traction, so it's able to move more. And that sort of explains the way that it ends up curving as it goes down. It's a little bit hard to describe, especially with that dark colored thing. Let's look at it with this. Okay, so here's a wavefront coming in. As it enters water, the part that enters the water first slows down. The part that hasn't entered the water still goes at its original speed. It sort of causes it to pivot, essentially. So we get the effect that as the light comes and it enters the water, it pivots and moves more vertically down. So this was Huygens' view. And, with the experiments of Young and Fresnel, basically nobody thought light was a particle anymore. Newton's explanations of colors and everything were nobody used them. It was just wrong and useless, and it didn't explain so many of the phenomena that the wave theory of light does explain. So the particle theory didn't come back until Planck, but then really Einstein. Planck was a little bit more reserved in 1900 when he made the hypothesis that light was emitted or absorbed by matter in individual packets, he still didn't necessarily fully believe that all light existed as like a particle or as a packet that we would call a photon today. Planck didn't quite go there. Einstein did. Einstein in 1905, his miracle year, his paper on the photoelectric effect, Einstein did say, yeah, you know what? Light really does come in particles while also behaving as a wave. So this is one of these famous conundrums that is one of the difficult things in quantum physics today. Is light a particle or is it a wave? Well, it depends on how you look at it, how you treat it. You know, if you're friendly to your neighbor will be friendly. If you're mean to them, they might be mean. You know, if you look at light in a way that brings out its, you know, wave-ish character, it acts like a wave. If you treat it in a way that you think it's a particle, it ends up looking like a particle. So it's kind of a funny thing. But so that's where that wound up. The gravitational waves, I'm not quite sure as much what to say about that. I mean, you know, incredibly faint. I mean, the idea is that a couple of, you know, stars falling in on themselves, you know, which is a huge process, is barely able to create something that even our most sophisticated equipment barely registers. It was one of the predictions of Einstein, and we found out that it's true, and I think that's interesting. I'm not sure what to say about the hypersonic front really at all. Not sure what to say there.
On a gravitational wave, for example, how do you know that's not a sound wave?
Well, so we measure these waves by like what effect they have. So like at first we have our bodies. So how do we know that something coming towards us is light versus sound? It's like, well, does it interact with our ear or does it interact with our eye? So like if you cover your ear, do you no longer hear? Okay, that means your ear's got something to do with the hearing. If you close your eyes, you're not able to experience something, and that's what we call light. So with the gravitational waves, you know, neither our eyes nor our ears work to hear it or see it or taste it or smell it or any of these other kinds of things. So what the experiment essentially does is it makes a very, very, very long path. And what it's able to observe is that the length of that path changes very, very slightly, like
I can't quite recall.
many orders of magnitude less than like the width of a proton. I mean, tiny, tiny change in distance. And this is over a path that's kilometers long. It's already a pretty long tube, essentially, and then they bounce the light back and forth on a mirror several times. So it really seems very long. And then the way they measure the change in distance is very clever. It's not like anyway. So that's just not related to vision. It's not related to hearing. It's that the distance between two places actually changes because of this gravitational wave passing through the apparatus. So the way they do it is they have it in one direction and they have a tube going perpendicular to it. And so the idea is that if you can get a sense of what direction the gravitational wave is coming from based on how much of an effect it has on this direction versus this direction. And then we've got a few of these around the world. Like that recent kind of famous one that got the big press it's in, is it Louisiana? Yeah, Louisiana and Washington State or Oregon or
The Northwest.
The Northwest. So, putting all that together, you get a sense that, yeah, it really happened. And that some rough idea of where it may have been, what direction it came from. But, we have to make this stuff better so that we have more of it and can get a better look. And then it's like a new sense organ that we have of now we can sort of hear these, black holes colliding several billion years ago, far, far away. So it's.
And the Chinese and the ESA, and I can't quite remember now if NASA has rejoined the ESA in the project, but at least these two space agencies are putting up space-based versions of the gravitational wave detectors within the coming few years. I forget the exact timeline. So we'll be able to have much more accuracy in measuring these things because we'll be able to measure them over much greater distances when they're in orbit.
Mm-hmm.
Good.
Okay, so why don't we go to another question that came in online.
Sure.
This is from Matt in Montreal. He asks, LaRouche has written that the entirety of what is called Euclidean space, and I think this follows well from Diane's question and what was just discussed. He said, LaRouche has written the entirety of what is called Euclidean space is constructed by nothing but circular action upon circular action. The entirety of the complex domain of Gaussian physics is also constructible by extending the application of Cousé's principle. So he asks, can you explain how this concept of circular action is at the base of geometry, as opposed to the Euclidean geometries practiced today? And also, can you say a few words on how either geometry impacts how we organize a society?
Okay. Take a few aspects on this. So one thing is that what makes circular action so special? Why is it such a, why is it all over the place? One thing is a very basic kind of action. This also, so when we were talking earlier about, the motion of the Earth around the sun, which I don't think we really fully came to an answer to, but I think that's actually okay to leave that kind of floating in the mind. I think part of the value of that question is that it seems obvious, but you actually probably can't answer it. Cousé, in addition to having pointed out in regards to astronomy that there's no point that could be so still that it couldn't have been more still, means that nothing is stationary, that nothing could move so uniformly that it couldn't move still more uniformly, and that uniform action couldn't actually exist as in the physical world. Cousé also looked at circular action as being different from other kinds of action in a way that's very similar to what Fermat did with light. So Cousé's reasoning was that a circle accomplishes a very specific objective. There's a few things. One is that you can't describe the length of a circle from the straight. You can't use straight lines to describe the length of a circle. Pi is incommensurable, transcendental. The other aspect is that when you create a circle, you're enclosing the most area with the least perimeter. Or if you made a sphere encloses the most volume with the least surface area. This is why if you blow bubbles, they make spheres. You never, even if you had a square-shaped bubble wand, I'm sure you've tried this, or like the star-shaped bubble wand, when you blow it through the star-shaped bubble wand, you don't get a star-shaped bubble, you get a spherical bubble. Why? Well, that soap is, pulling on itself. It doesn't want to get stretched out any more than it has to. And so the shape that lets it hold all that air that's in the bubble, while also being as relaxed as possible, as least stressed out and stretched out, is to make a sphere. So that's why bubbles do that. So among shapes, it's not just a shape that we describe by how we draw it. It also has a physical connection in achieving something with the least effort. So in a certain way, it reflects the concept of principle itself in a similar way that the golden section does. The golden section, or the golden ratio, you may have heard of it, or expressed by the Greek letter phi, which we're told exists in Greek architecture and pine cones and the human body and the ratio between your head to your belly button and to your feet. And it does appear in all these places. Similarly, the reason that occurs is that the divine proportion, the golden ratio, is actually the simplest of all proportions. It's a way of dividing a line, cutting it somewhere, or having a line and growing it in a certain way. It's the least arbitrary way of growing something. And so in that way, it really reflects growth itself. And I think this is why we see it in life. Similarly, the circle reflects principle itself, which is why we see it in playing a very essential role in geometry. You look at all the constructions that you can do purely with circular motion, with the compass. You look at the fact that even in different curved surfaces, although shapes can get deformed and all of this, angles don't. Angles locally, a circular rotation, even when you transform it geometrically, it maintains its uniform circularity. It's kind of hard to, I'm trying to think about how to describe that in a way that works. Maybe I'll say that, though. It is true. And so then this comes up in the complex domain. One thing about the complex domain, based on the survey responses, I know that there are some people who would be interested in learning more, getting your hands dirty, or working on Gauss. So I'll be sending out an email about the specifics, but we can do a 3 or 4 90-minute class series for a contribution of $100 to go through the complex domain, an online course on that. But the way Gauss's complex domain works is that it shows that there's something about number itself, the most, basic and unavoidable aspect of number, that inherently includes rotation, circular rotation. So it's an unavoidable aspect of number, and it appears like a principle in that it achieves something in the best possible way. So it really sort of embodies intention, which I think that kind of says something, that's then such a basic part of our physical world.
Just quick, just looking at an email that came in just quickly on, because you ended with the idea of intention or purpose. Anne in Denmark wrote in about the issue of Claire Sellier's objection to Fermat. And she said, if it's correct when Claire Sellier says the principle of least time is a moral principle, not a physical one, and that this principle of least time can therefore not be true if that's his idea, but it's also correct that light actually does move according to least time, is not that the proof? That she's saying that that the physical principle of least time is guided by a higher principle, a moral one. So,
well, yeah, the fact that it works, that's definitely got some marks in its favor. I mean, compared to Descartes' theory, which was wrong and didn't work. One more brief thing about that, I know we got a question in Manhattan, is that Maupertuis, who is one of Leibniz's opponents, supposedly developed the idea of least action. He's the one who's credited with discovering it as a principle. Now, action itself as a concept was developed by Leibniz as a physical magnitude. Maupertuis, in his work on least action, actually claimed that he used least action to prove that Fermat was wrong, that light actually moved faster in water, based on his supposed idea of least action. So even that phrase, least action, has meant different things at different times, and has been, taken up. But yeah, and that's a very good point. Least time works, so that stands in its favor for sure.
So why don't we go to Manhattan for their question there?
Good afternoon.
Yep.
I would like to know which wave, particle or light wave, can be slowed down and even stopped or frozen to store information.
You know what? I heard about that, but I'm not quite sure how to answer you. I mean, I don't believe that it's possible to distinguish between light being a particle or a wave. So one aspect of its behavior might be used in that, but I'm sorry, I just don't know. Do you know how to? I've heard about that in the news, but I couldn't really give you an answer on that. I'm sorry.
It's okay. We're still working on it.
Okay.
Maybe I can just make one brief comment, not directly on your question, Bruce, but reflecting back on what Diane was asking. I think the fact that you really can't determine by its behavior if it's a particle or is it a wave, and some of the other things we were just talking about with gravitational waves, I think it does show that we really are on the cusp of recasting our view of the universe, new principles that have to be discovered to allow us to actually understand the real principle of what these things are and how they really behave.
Yeah.
We're seeing a certain paradox in the language that we use.
This is one of these things where, this is an interesting case because supposedly, and this is what really pissed Einstein off about the quantum mechanists, is he said, we're not done. We're not done. And he got along with Bohr personally, they were friends, but he said, look, you know what, you're just not right. Basically Bohr's view was that we've figured it all out. You know what? Quantum mechanics really says everything you're going to be able to say, and that's just that. And interestingly, I mean, there have been experiments like the Bell inequality was used through experiments to try to show that they're actually. So the quantum mechanics stuff goes in an interesting way because it makes the claim that there no longer is a reality independent of observations. That our observations are real, but what occurs in between them isn't actually in one state versus another. It's purely a realm of probabilities and possibilities. And you can lay out what probability, what likelihood is that something will happen, but that it's really impossible to know exactly what will happen. And as far as the experiments on this go, that seems to hold up. Now, one place I would look at it in an interesting way, I think, is the human mind. Given that we have, clearly we have brains, and obviously our brains are related to our personalities and our thoughts, while at the same time our thoughts are not equivalent to our brains. So, I think the quantum stuff is an interesting kind of angle to look at about how a process that seems to have a certain randomness to it, maybe when it's ordered by a higher principle, such as cognition, no longer appears as random. Like take music, for example, and animals. I've done a huge amount of experiment with this, but as far as I can see, most animals don't really get musical ideas. It doesn't happen. Some of them, they like music, they like sounds, that's for sure. But like a piece of music really making a point, or maybe if there's something funny in a piece of music, animals aren't laughing at that. They don't get it. So even though there is something going on there with music, if you tried to understand music, if you tried to say, I want to figure out what makes Bach a genius, what did Mozart do? What did these composers do? What's the secret to Clara Schumann? The way to find out is not to, put headphones on dogs and parakeets and then watch how they respond to it. You're not going to learn something about music that way. And so I think that something could be similar with the quantum stuff, where the kinds of apparatus that we're using, non-living, simply is incapable of picking up or resonating with something that really truly could exist there, just as music doesn't resonate in that way with animals. I believe that the quantum stuff will be undetermined until we're able to really have those experiments tie in with biology, and then especially with the human mind, because any physical theory that's unable to explain our existence and our ability to discover how nature works and change it, it's a very incomplete theory, to put it mildly.
Good. So we have another question that came in via email, and this is more, I guess, on the on science policy than that aspect of it. So Derek asks, have you considered how you would implement a fusion driver program on a global scale without treating the world population as a conglomerate? Meaning, if you could make a fusion torch or a fusion power plant ready for shipment tomorrow, how would you implement it with the world population, considering sovereign governments and, most importantly, where the country is currently with respect to GDP per capita? In other words, would we expect a caveman to start living like the Jetsons overnight?
It seems like part of the question here, because one of the premises of that question is, if we had a fusion power plant ready for shipment tomorrow. Okay, so first off, that's wonderful. If we've got that, that's the happiest day ever. That's great. And then the question is, are different countries going to be able to use it? Now, I don't think this is the intention, but it sounds a little bit like, look, if we had that, the goal would just be, let's get that everywhere. Let's build these fusion plants all over the place. If countries lack the technical know-how at present to operate or produce them, that's fine. If we have enough people from the countries that are producing it, they can go and operate it for a few years, and everything's all set. Like this is the case, just to take an example, Africa. So this past week I was at a conference in DC about China and Africa. And one guy got up to ask a question. And he said, China's building this electric train, in Ethiopia. And are they able to handle an electric train there? I mean, maybe they shouldn't have sold them that. It might be too advanced for them. Which, I mean, obviously there's a lot of overtones in that kind of a statement. But how does something like that work? How does technology transfer work right now? What did Eisenhower intend with Atoms for Peace right now, for example? So anyway, the way that kind of technology transfer works is that initially, along with the technology itself, is you do have to bring in a team of people who are able to do needed maintenance or engineering. And then, it takes some time to build up, a local reservoir of knowledge about how to use that, to them, new technology. So I don't think that if we had a fusion plant ready to go tomorrow, I think it'd be pretty similar to the ways that this has been done with plenty of technology transfer already. So I'll stick with the first response, which would be that would be the best news ever.
Maybe I can add something to it. We don't have a fusion torch tomorrow, but so what's the process that would bring that about? What's the process between now and the point that we do develop that, of agreements between countries, cooperation in national labs between China and the US, and then also something that China is doing especially is bringing younger people in from nations that don't have a tokamak in their country to come work on in the Chinese tokamak or the Chinese space program to extend the scope of it. You bring people in from other countries that don't have the apparatus in their country quite yet. So think about that process of international cooperation that's going to contribute to making the scientific breakthrough to begin with. So the world that finally does build a fusion torch ready to put into service is going to be a different world than the one that we have today. So why don't, looks like we have another question in Manhattan. Why don't we go there?
Okay. This is based on what Jason was saying about the golden section. I was wondering why you're saying that the golden section is the least arbitrary form it would take. Because how I think about it is that when I've looked at the golden section, it goes into this kind of growth spiral in the universe, and that is the basis for why it's that. And my question is basic on what you're saying. Why is it the least arbitrary?
Sure. So this is very roughly, it's kind of easy. Okay, so this is not precise, but with this line, I've split this piece of paper into two components. There's a lot of places I could have put this line. Now, one non-arbitrary way to split it would be to split it down the middle. So maybe I should say, besides equality, the golden section is the least arbitrary. Maybe I should say, if we plan to have change, the golden ratio is the least arbitrary. So let's say this is our among all the ratios that we could have, maybe we could split it like over here. When we make two pieces, we really create three things, right? We got one piece, a new piece, and the whole. So maybe this could be thought of as, as we had this much, then we add a bit more to it. Or we began with this component and we added this to it. We're growing. The golden ratio is the one where the description of what you've created is as simple as possible and involves the least number of numbers, namely 1. So let me give a counterexample. So let me divide this line into thirds. Okay, so we got, it's kind of mirrored. Okay, there we go. Oh yeah, let me draw the other one too. All right. Okay, so here we go. We got it cut into thirds. We've now got the initial component, right? A longer piece, and then the whole thing. The numbers that I would use to describe this are 1 and 2 and 3. That's 3 numbers. If I split it into a fourth, I would have the numbers 1 and 3 and 4. If I cut it 2/5 along the way, I'd have 2 and 3 and 5. When you split things along the golden ratio, the only real numbers that you have are 1 and the golden ratio. That is, so let me look back at this. So just in terms of what this golden ratio is, for just make sure everyone's aware of it. Okay, the ratio from the small piece to the large piece is the same as the ratio of the large piece to the whole. So like 1 and 2 and 3 Well, 1 and 2 is doubling, 2 and 3 is not doubling. It's a different ratio. Here, the small piece to the big piece, and then the big piece to the whole piece, same ratio. The whole thing is really described only with one ratio. And therefore, it's the simplest way of dividing something in that it has the simplest description. Any other way of doing it, like 2/5, leaves you with 2 and 3 and 5, which 2 to 3, 3 to 5, these are different ratios. So why did you choose that one instead of another? To answer Kepler's question, why so and rather than otherwise? The golden ratio, I can say, I'll tell you why this rather than otherwise, because it's the simplest growth, the simplest kind of division or the simplest kind of growth, because there's just this one number that characterizes that growth.
Okay, it looks like we have a question in the conference line, so let's go there and see if this works. Okay, so can you hear us?
Hello?
Hello. Yes, I have my question.
Go ahead.
My question has to do with. Hello. Yes, this is Osvaldo from Denver.
Hi. Go ahead.
Turn
Yes,
off
with
your
the question
computer
with
speakers,
regards
just talking to the phone.
The technology and they're having ready a plant for shipping has to do. It's very important to understand that the technology is different from the knowledge of how to build that plant or the principles involved into developing the plant. The fact that people does not understand fusion energy impeded the Americans to accept just shutting down the production of all those plants that were ready to be built here when John Fitzgerald Kennedy came, or the Germans in Germany accept the shutting down of their power stations, nuclear power stations. There was a movie that scared everybody about the meltdown of a reactor way down with a very known actress. Well, this is my question, and what is your comment about it? Thank you.
Yeah, it's true. I mean, we're not just gonna have a fusion reactor one day without having gone through the work of developing the science and the technology behind it. I guess maybe two ways. One is to build on what you're pointing out, Megan, about what would it look like to, really have a driver to make that a reality. I mean, some of this stuff, it's like you can just tell there's no intent really to make it happen. I mean, if the plan on ITER is to finish it in what year now? Like, every year it gets pushed back a year.
First plasma is 2025 now, but
2025.
maybe later if
Okay.
the U.S. doesn't fund it.
Okay. All right. So 2025, we're supposed to, ITER is supposed to get started. There's the plan for the next larger thing to build after ITER is essentially already worked out, the demo reactor. So this would finally be a fusion reactor that would actually make energy using the very antique technology of getting something hot and then using that to create a phase change and then blow a gas through a turbine. So if the intent was to really make this happen, if this was like a full-on effort, we're not going to have ITER finally make its first plasma in 2025 and then demo some 10 years later. It would really jump in to make it happen. So this is the sort of thing where you talk about like a crash program where you say, we're going to make this happen. Like in World War II, with the terror that Adolf Hitler was working on or going to achieve a nuclear weapon, that was a pretty big incentive for the U.S. research for the Manhattan Project to figure out how to do that. Kennedy's mission of going to the moon, well, he put a huge amount of resources into making that a reality. If we just sort of dawdled along to see if we'd ever get there, wouldn't have happened. It was an intent saying, we're going to make this happen. And so if you think about what kind of priorities exist around the world, Or, in the United States, what kind of priorities do people, like, what do people think is a priority? I'd say what should be a priority, building up our infrastructure, employing millions of people, building a new platform of infrastructure, putting money and resources into fusion research. If you think a better priority is making sure Russia doesn't meddle in elections again, if that's your idea of what a priority is, then you've got no vision. You got no vision for the future. So, I think that goes with with LaRouche's 4 laws. I mean, this is one economic concept as expressed with 4 facets, right? We need Glass-Steagall to end the gambling that's going on. The way that people just chase very quick profits with your money, okay, that's got to go. We need to have a national bank because any other kind of financing is just unable to be in coherence with the kind of value that an infrastructure platform makes. It's just not like a private investment. It's just different. And a national banking approach is in coherence with that. So you have to. It's a basic economic principle. You got to have specific economic goals, not just pushing money around to make money. And most specifically in that, in his 4th law, is that a crash program on fusion, on space research, this really has to be a uniting economic front. Because I'll tell you, things are going to, people who keep claiming that China's going to collapse any minute now, that's geopolitics. That's really wrong. But I'll tell you, there is a limit to what the human species can do without moving to a new form of power. There is a limit. China's not going to hit it like next year, like some people wish. That's not going to happen. But as a human species, we do have a limit there. And removing that barrier, opening up, breaking through that ceiling to the next level, that's got to be our main economic focus. Yeah.
Well, I'm going to use that as an opportunity to wrap up questions because we have a few things to say about next week's class. So, would you like to say those things?
I'll say those things about next week's class. Yeah. So for final exam, remember the point of this. So what's this class series titled? What is the new paradigm? What's our objective? To end geopolitics. So I'll tell you what, for your final assignment, not going to be to write an essay or do anything like that. The final assignment is to go out and do something to make the new paradigm and do something you haven't done before. Preferably, and probably unavoidably, something that makes you feel uncomfortable. If it doesn't make you feel uncomfortable, you might not be pushing yourself. And the fact that sometimes going out and making things happen feels very awkward or difficult, that's not you. That's the fact that you're living in a decaying society, at least for most of the people who are tuning in on this, not in China. So, what does that mean? Get out, print some copies of the latest LaRouche PAC leaflet. You may be watching this later, so I won't give one by name, but, get that and then print it. Go out and get it out. In your local downtown, by a post office, a farmer's market, go out and get it out to people. People are interested, get their names and their phone numbers. Send them back. We'd be happy to help work with you on follow-up. Call into a radio talk show. Say something. Go to a meeting in your area, some political meeting, a congressional town hall meeting, a meeting on some subject. Go there and speak up. Hopefully it's a meeting where, this is particularly relevant. That would be even better than just attending a... Okay. If you would like to translate our material into a language we don't currently translate it into, volunteer. Any of these things would be helpful. But for the final exam is do at least one of these things this week. Do something new that you haven't tried before to end geopolitics, to make a new paradigm a reality, to engage more people in understanding what that new paradigm entails and to move on it. Do one or two things of that sort that are new for you and report back. Say how it went. We are very hopeful, it's not confirmed yet, but we are very hopeful of having Helga Tsepp-LaRouche on as our wrap-up speaker next week. So if we've got a lot of insights and questions and successes and, just advice needed about how to organize, that would be an ideal way to pull together the different strands that we've covered over the past few months about the nature of geopolitics, the philosophy of geopolitics, and how different cultures are acting to overturn that, and how science can pull us together as a unifying mission for our species. So go out and make it happen, and tell us what happened when you tried and succeeded or had difficulties. And be prepared to discuss that. That'll be our topic for next week.
Good. Well, thanks very much, Jason, for that follow-up. Thank you very much, our audience in Manhattan, for your participation. And as Jason said, get ready for the next final class of the class series next week. Get ready this week to carry out your homework assignment, and we will see all of you very soon.